All right, good afternoon and welcome to this week's Iowa Learning Farms Conservation Webinar. My name's Matt Helmers here at Iowa State University. Fortunate to get to moderate our webinar today. So I want to welcome everyone. And today we are very fortunate to hear about a really important topic. And a question that I think many of us get is, can long-term soil health practices improve water quality? So we are really fortunate to have two researchers from Ohio to talk to us about that. We have Dr. Vinayak Shedekar, that's a research scientist with The Ohio State University. I have to make sure, or Vinayak will chastise me for, or criticize me for not getting "the" in there. So from The Ohio State University, and Dr. Will Osterholz, that's a research soil scientist with the Soil Drainage Research Unit with the USDA Agricultural Research Service in Columbus, Ohio. And I believe Dr. Osterholz is an alumnus of Iowa State University, if I'm not mistaken, working with Dr. Matt Liebman on a number of extended rotation projects. If I'm not mistaken, he can correct me if I am. So with that, I will turn the virtual floor over to Vinayak and Will. And as always, if you have questions, please type those in the chat box and I will get them to our speakers at the end of their talk. So with that, I'll turn it over to Vinayak and Will.
Thank you, Matt. It's a pleasure to be part of this group here as part of the Iowa Learning Farms webinars. Thank you for inviting us to the webinar. And the way we're going to do the presentation today is Will Osterholz he's going to talk about the soil health component of the project that we're going to present here, and then towards the end, I'll talk about some of the preliminary results that we have seen from the water quality monitoring. Just before we get started, I wanted to just make a couple comments here. We're just starting to scratch the surface of this topic area. So especially looking at the long-term implications. So the whole idea behind this work that we're doing here in Ohio was to not just look at soil health as a singular practice, but really try to relate that with the time scale at which that practice is conducted. And if there are farmers in this group who have been using no-till and cover crop type of practices over time, can vouch to this, that it's a very slow transition that you experience over time. And a lot of times the way we conduct our research is such a short-term research that we kind of miss that opportunity to be able to study those systems over time. So with that, I think I'm going to have Will take over from here and kind of lead us into that more discussion on how the long-term aspect really relates to our work that we're presenting. So with that, Will, take it over.
Okay, thanks, Vinayak. And thanks, Matt. And yes, you are correct. I am a proud alumnus of Iowa State. Spent a number of years there in Ames working with Matt Liebman and also Mike Castellano. So some fond memories of Iowa. But now I'm in Ohio working with Vinayak, and I know we have a lot to get through today, so I'm just going to kick it off and try to move through some of this pretty efficiently. So Vinayak, you can go ahead there. Yep. So as I'm sure you're all aware, there's been more and more research coming out in recent years showing that both cover crops and no-till can improve soil health, especially when they're combined in a system. And this is really the core of what people are now calling regenerative ag. We're still kind of referring it to soil health management. So there's different names for it, but really the core of this is cover crops and no-till. And so these are some older results from actually one of Vinayak's projects here in Ohio, where they looked at some different soil health indicators in a few fields that varied by how long they had been in this type of soil health management. So you can see the bars on the left are showing conventional field without any cover crops or no tillage. And then as we move towards the right, these fields get more and more sort of mature is the term we've been using in terms of how long they've been under this management. The idea here is that if you're consistent with this management, these benefits can accrue over time. We know that soils can take a long time to respond to management, and so what we can see is that as this management has been in place for longer periods of time, we see increases in soil organic matter, so improved soil health as these systems mature. And then on the right, this is showing a biological indicator. This is just the fungal and bacterial biomass in these different fields. And we can really just focus on the bars, the size of the bars here, showing you're getting increases in microbial biomass as these systems mature over time. So we know that this is the case, that cover crops in soil and no-till can improve soil health. Vinayak, you can go to the next here. But the bigger question that seems unanswered here is, does good soil health necessarily lead to improvements in water quality? And it's actually, this is a big question, and one that I feel like has been assumed to be the case by a lot of different organizations, but there's actually very little evidence to support this idea. So this is one of the main goals of the work we're sharing today, is to try to answer this question: does good soil health also equal good water quality? And then a secondary question here is, does it matter how long the soil health systems have been in place? So I was just talking about this idea of maturity of management. And so does it matter if the soil health systems are mature versus a more transitional or a more recently implemented set of management practices? Okay, Vinayak. All right, so, and by water quality, we're mostly referring to nutrient losses. So both phosphorus and nitrogen in Ohio are a big deal. Phosphorus runoff into Lake Erie is a huge environmental issue in Ohio. And then, of course, Ohio also contributes a lot of nitrogen to the Gulf of Mexico. So we have also concerns about that whole Gulf of Mexico hypoxia issue, as I know it's a big issue there in Iowa. So that's what we're really talking about in terms of water quality, is mainly this phosphorus and nitrogen loss. So to these ends, we've begun a research project over the last year and a half. This was funded by North Central SARE. We're calling it Soil Health and Water Quality Nexus in Sustainable Agroecosystems. And there's a pretty big team here involved in this project, both from Ohio State as well as USDA. So we'll be sharing some initial results from this project. We're still obviously actively working on this research, but we're going to show sort of where we're at right now in terms of what we've learned. And sort of the cool part of this project, and Vinayak was mentioning this earlier, but we're really focused on this long-term implementation of the soil health systems and how those systems influence both the soil health side within the field, but also water quality outcomes at the edge of the field, so nitrogen and phosphorus losses. So we have 3 locations we've been working at in this project. Today we'll just be focused on 2 of these, the one here in South Central Ohio, DB, and then the one in the very northwest corner of the state, the DM site. Okay, Vinayak. So this is an aerial view of these 2 locations. So at each location, we have 2 fields. These are paired fields, and one of them is under conventional management. So at the South Central Ohio site, it's this MH field. That's our conventional field. And then at Northwest Ohio site, it's the SJ field. That is our conventional field. And then the DB field and the DM field would be the long-term soil health fields. The soils at these sites are a little different. The South Central site, it's silt loam soils. So they're called Bennington and Cardington. That probably doesn't mean much to you guys in Iowa, but they're not so different from some alpha sol type of soils you might see in the eastern half of the state there. Somewhat poorly drained. All 4 of these fields have tile drainage. So that'll be important when Vinayak gets into the water quality results. So South Central, similar maybe to some of the Iowa soils. The Northwest site, they're a bit sandier, so a bit coarser texture than you might see there in Iowa. And Vinayak's also going to talk a little bit more about the management, but at this point, I just want to point out that the conventional field management, it's pretty similar to what you'd see in Iowa. It's corn soy rotation, tillage in that rotation as well. Not inversion tillage, but something like a chisel plow would be used in most years. And then for the soil health fields, these also have corn and soybeans, but they'd also include wheat, winter wheat in the rotation. And then they'll have cover crops following the corn and the beans. And both of these are no tillage. And by long-term, we really do mean long-term management. Both of these fields have been in this sort of soil health system for more than 30 years. So they're really about as long-term soil health management as you're going to find around the Midwest, I think. So a pretty good example that we were able to find. All right, Vinayak, move on. So we've been working on assessing the soil health status of these fields, and we have a number of different measurements we've been taking. You can see them listed. Today, I'll just be showing results from the 3 that are bolded here on this list. So we're going to look at organic matter, we're going to look at carbon and nitrogen enzyme activity, and also the wet aggregate stability. And just to be clear, we took these samples in the fall following harvest using a hydraulic sampler. Can talk more details about that if you have questions, but I think we'll just go ahead and jump into the results. Thanks, Vinayak. So first results here, we're going to look at the organic matter at our South Central Ohio location. So on the vertical axis, you can see we have A, B, C, and D. Those are different depths. So we split our samples into different depths to see if there was an effect of the no tillage on stratification within the soil. So we've got 0 to 2 to 6 inches, 6 to 12, and then the 12 to 24 inches. And then within each of these depths, you can see 3 different bars, 3 different colors. The yellow bar is showing the conventional field. Then the brown is showing the long-term soil health. And then the green bar, I didn't mention this, but we've actually been taking soil samples in some old woodlots near these farms. And we're doing that because we're interested in what these soils might look like in a more natural state, to sort of get a upper bound on, what type of soil health measurements we might expect to be possible at some of these sites. So if we look at these 3 different, the 2 fields and the woodlot, the most obvious thing is that the woodlot has much higher organic matter, especially in that top 2 inches, which is what you might expect. But if we focus more on comparing the conventional field in the yellow and the soil health field in the brown, we can see there isn't an increase in organic matter in the long-term soil health field. Now, it's not huge, but it's definitely there. And I think for this South Central Ohio site, we can say that the long-term soil health management has increased organic matter. And it's kind of interesting that it's been an increase even down to the 24-inch depth. So pretty much throughout the profile that we measured, we saw at least a slight increase in organic matter. Okay, Vinayak, onto the Northwest Ohio site. So again, this is organic matter but now at the Northwest Ohio site. So here we have the same sort of color scheme. The woodlot in the green, you can see much greater organic matter than either of the cropped fields. But now if we compare the conventional field in yellow and the soil health field in brown, at this site, actually, the conventional field had greater organic matter, which we were surprised at. But we looked a little more closely, and it turns out that the long-term soil health field actually has some more sandy type of soils. And so what we think is going on here is that those sandier soils, we know that they tend not to accumulate organic matter as much as more of a loam type soil. So we think it's that sort of inherent difference in soil texture between these two fields is what's really causing this difference in organic matter. Okay, Vinayak. So now let's look at some of the enzyme activity results. So enzyme activities, if you're not familiar with that measurement, it's an assessment of biological activity, particularly with the different nutrient cycles in the soil. So enzymes break down molecules in the soil. It's part of microbial decomposition process. So if you have higher enzyme activities, generally we would consider that a healthier soil. So we're looking for bigger numbers, means a healthier soil here. So on the left, we have beta-glucosidase is our enzyme, and that's an enzyme that's very common, and it's heavily involved in the carbon cycle, breakdown of organic matter. And so what we can see at the South Central Ohio site is that, again, the woodlot had the highest value. So we would call that the healthiest soil. And then if we look at the brown bar, which is the soil health field, compared to the yellow bar, the conventional field, we do see an advantage to that soil health field having more beta-glucosidase activity. And then on the right, we have beta-glucosaminidase. That's a mouthful, but that enzyme is involved in the nitrogen cycle. So this would indicate, more nitrogen cycling activity, potential greater activity of organic nitrogen being broken down. So here again, we see that the green bar, the woodlot, is higher than either of the cropped fields. But now there's really not much difference between the soil health field and the conventional field. So this was a little surprising. We think probably what's going on here is that both of these fields are not limited in the amount of nitrogen available for microbial growth. And so they're both sort of holding steady at a similar level. So probably not much nitrogen limitation going on in either of these fields. All right, Vinayak, we'll look at the Northwest Ohio enzyme activities. So again, the same setup here as the last slide, where we have the carbon cycling enzyme on the left and the nitrogen cycling enzyme on the right. Again, the woodlot really pops out as having the greatest enzyme activity, both for the carbon enzyme and the nitrogen enzyme. But now here, when we compare the yellow conventional field with the brown soil health field, in this case, we saw a similar pattern to what we had for our organic matter results, where that conventional field has better soil health according to this enzyme activity metric. And again, our best guess is that this is related to that difference in texture between the two fields, where it's just a sandier field at that long-term soil health, that brown bar. All right, Vinayak, I think I've got one more soil health slide here. So this one is water stable aggregate results at our South Central Ohio location. So this one is set up a little bit differently. So I'm gonna just explain the bars here. So each bar in this graph is showing a different field. So at the top, you can see the conventional field. So that's the same conventional field we've been talking about. And at the bottom, that bar is showing the long-term soil health field, the very bottom. And then the one in the middle here is a different field we haven't talked about yet, but this is a neighboring field that the same farmer who does the soil health field has recently started farming this field, I think in the last 5 years. And so we're calling this one the transitional soil health field. And we were curious about that one just to see how the soil health properties were developing over time. So, over that first 5 years maybe of management versus where the long-term one we've had over 30 years. So we're seeing how quickly that soil health might manifest in that transitional field. And then to explain this aggregate measurement a little bit, basically in a healthy soil, what we want to see is a lot of large, stable aggregates. So in the way this graph is set up, the large aggregates are shown in sort of the diagonal crossing here. It's that 2 millimeter size class. And then we have smaller aggregates, 0.5 millimeter or 0.25 millimeter. So in a healthy soil, what we want is a lot of aggregates in that large 2 millimeter size class. And so that's the portion of this bar we should really be focused on. And what we can see is that in both of these fields that are under soil health management, we did have more of those 2 millimeter large aggregates that would suggest improved soil health. So that is what we'd expect. And kind of exciting that, we saw that even after just a few years of management, that we were able to see a similar improvement as after 30 years. So for any of you farmers or people out there promoting soil health, worried about if it's going to have a rapid impact or not, at least in terms of aggregates, we were able to see that that impact of management even after just a few years. So that's a little encouraging, I think. So that's all I had for the soil health. So I'll hand it back to Vinayak. Hopefully I left plenty of time to get into some of these water quality results because they're exciting.
Thank you, Will. I guess if we do have questions, I guess maybe we'll just hold on to those questions until I get through my slides and then come back to it. Just to explain so in-field soil health assessment was one component. The second component was the edge of field water quantity and quality monitoring. So this is a typical edge of field monitoring setup. This work is, this photo was taken when we were still trying to set up this site, but gives you a good idea of what it involves. Essentially, we identify a location within the field where majority of that surface runoff is kind of concentrating and coming out, leaving the field. And we put a H flume at that point where the surface runoff, the surface water is leaving the field. And we try to have the ability to measure that. You don't see this in the picture, but there is a subsurface drainage or the tile drainage outlet that comes out from this field. And the second box that you see here is linked or connected with that tile outlet that comes out of this field. So we have the ability to monitor the majority of the water loss from that field through surface and subsurface pathways. Of course, the instrumentation that's involved in here is automated samplers that take water samples at a certain time interval, and also some flow proportional sampling during high flow events. And then we have the ability to measure the water flow or the depth of water going through these structures at a 10-minute interval. And then our samples are typically composited over 2 days, but we do take aliquots every 6 hours during the base flow conditions. Quickly, Will explained this earlier, the paired field study. So in the long-term field at that south central site, we have a flume that sits here and then the tile outlet in this corner. This was a relatively larger contributing area compared to the conventional field that's paired with it. But this just kind of gives you an overview of how our monitoring looks like, again, in terms of those flumes. So I think you saw this in the previous picture as well, but just wanted to bring up, as we are monitoring this for water quantity and quality, we also have these visual observations that we just can't ignore. And these are some of the more impactful observations in a way. It's interesting to see how clean our flume looks in the field that's been under that long-term soil health practices, and the level of surface soil erosion that we see in the other field that does not have any ground cover, and then just it's just amazing amount of soil loss that we see after especially major events. We, as of now, we're not really quantifying that loss as part of this project, but certainly intend to in future. And I wanted to start with the loss of water, or just the quantity of water, how that compares across these fields. So what you have here is rainfall. This was about a 6/10 of an tenth of an inch rainfall event in the month of March that happened. The red hydrograph, which is basically the discharge rate that we observed in tile drain outlet at the field that's under no soil health practices. And the green line is our field that's been under long-term soil health practice. And you might see, or you see there is about 33,000 cubic feet of water leaving that field as part of, in response to that rainfall event. And then there is more water leaving the soil health field. And one might wonder, well, that doesn't make sense. So, but if you normalize that based on the contributing area, and then convert that into percent of water leaving with respect to how much water came in, about 50% of the rainfall was getting out of that tile outlet from that conventional field, compared to only 28% of that rainfall event showed up at the tile outlet in the long-term soil health field. And you can see the response here is pretty slow, and some of this is has to do with the fact that it's a larger contributing area. But it's really unique to see how the hydrologic behavior of these fields is so unique. So moving on, this was the tile drainage component. You kind of see similar behavior when it comes to surface runoff, and this is where, a lot of anecdotal evidence, or a lot of times we do recognize the fact that fields which have standing cover crops or a lot of residue tend to slow the water down, and hence reduce the surface runoff amount. So we are seeing similar outcome here based on that one event where which was mainly driven by snow melt, but you do see a larger response in that conventional field compared to the long-term soil health field. So of course, this is just one or two events that we're talking about. So we're going to start looking at the 1 calendar year of data. So when you take the total amount of water leaving the fields, and just to orient you here again, this DB site is our long-term soil health field, and then the MH site is the conventional field, which is under the conventional tillage, typical corn soybean rotation. The blue or the greenish bar that you see here is the tile drainage portion of the water loss, and the orange bar component that you see is the surface runoff component. And you can see that the total water leaving that DB field, which was under long-term soil health, was about a couple inches less on annual basis than the field that's under conventional drainage, which is a pretty significant difference when it comes to the hydrology of these fields. And then if you look at the other pair here, which I'm hoping the animation would work, this is that other pair from Northwest Ohio. Again, that long-term soil health field compared to the conventional. And you can see that there's no orange bar here. Basically, we didn't observe any runoff in that year. And some of this has to do with where the flume was placed, but very negligible amount of runoff that we observed in the field that was under long-term soil health compared to the other field that was under conventional system. So we're seeing a consistently less amount of water leaving. So coming to the results that may be of more interest for our communities in Iowa, which is the nitrate loss. And here is the data on nitrate concentrations observed in the surface as well as tile. So the orange is surface runoff, and the greenish blue is the tile drainage. Again, that DB, the long-term soil health field, is on left side, and then the conventional field is on the right side. And you can see there is some differences in the nitrate concentration still below that 10 ppm threshold for drinking water quality. But this doesn't necessarily give you all the information unless you can multiply the concentrations by the amount of water that's leaving and to get the nitrate loading in pounds per acre. So this is the nitrate loss from the long-term field in terms of pounds per acre compared to the conventional field. And what is that? About more than 12 pounds per acre difference. And again, realize that this is tile drainage and surface runoff together. And you can see a majority of the nitrate loss is through the tile drainage, but you can see the huge difference that you see in here. And it's very consistent across this field, this pair as well as this pair here, the South Central as well as the Northwest Ohio, consistently lower loads of nitrate. And this is not something that we don't know already. A lot of other studies have kind of similar conclusions that nitrate losses are significantly reduced from fields that are under cover crop, especially cover crops, especially because of the uptake that happens during the non-growing season. Will helped us put this together. This is a lot of Dr. Kevin King, the USDA ARS unit here has about 40 agricultural fields that they monitor under their edge of field monitoring network for water quality. This is all the edge of field sites, the nitrate loading, annual nitrate loading from all these edge of field sites. And you can see a huge variability in terms of pounds per acre of nitrate loss. But if you put our sites on the same scale as what we see as a spectrum, both our paired sites are kind of on the lower spectrum of that nitrate loss. But within that, you still see lower nitrogen loads from our long-term soil health fields. So that's kind of a really unique and exciting observation. When it comes to dissolved phosphorus loss, this is dissolved reactive phosphorus loss. A lot of the literature tends to suggest that the stratification of phosphorus under a no-till system in the topsoil, the presence of the residue on the top, and especially the cover crop residue on the surface, has the potential to increase the DRP losses or the dissolved phosphorus losses from your surface pathways. And we do see some of that signature here. We see elevated dissolved phosphorus concentrations in our field that's under no-till, long-term no-till and soil health practices, especially in the surface runoff. For the tile drainage, you can see they're very small concentrations across both fields. Again, and this is where that hydrology plays a role, but if you multiply the concentrations by the amount of water leaving, in total, we're still seeing less amount of dissolved phosphorus leaving the long-term soil health fields compared to the conventional fields. And again, if you look at the results across that other site in Northwest Ohio, we're seeing very similar trend, that very small amount of dissolved phosphorus leaving that field that's under long-term soil health compared to the one that's under conventional. So this was kind of more exciting finding because of the fact that it's kind of counteracts with what the literature says. We are seeing something of that consistent with the literature in terms of the concentration data, but the hydrology plays a role, and we're seeing a little bit less dissolved phosphorus load. again, putting it on the same scale with what we see across the spectrum in Northwest Ohio. Majority of these 4D fields are in Northwest Ohio. And you can see there are many fields that have elevated surface as well as subsurface phosphorus losses. And a majority of these that you see tend to be the fields where there is very high soil test phosphorus levels, or the fields that have more frequent application of a nutrient source like manure. So, but on that spectrum, we see that our sites are kind of like on the lower end of the losses for the dissolved phosphorus. And then finally, the total phosphorus leaving these fields. As I mentioned, you do see that somewhat more higher concentration in surface runoff because total phosphorus is mainly dominated by the sediment-driven phosphorus transport. So we do see some elevated concentrations regardless. But if you kind of bring it into the loading equations, then we do see lower total phosphorus loss from our long-term soil health fields compared to the conventional fields. Again, very similar trend in terms of total loss. The long-term fields are just really helping minimize that total phosphorus loss. You can now here you can see that the huge difference in that TP loss through the surface runoff and even the concentration differences that you see across the samples in a year. So with that, I know this was probably too much and we're kind of switching back and forth between the two fields. So in general, here is what our preliminary results suggest. In general, we're seeing about 2 inches of water, less water, leaving the fields that are under long-term soil health fields. About 12 pounds of less nitrogen leaving these fields, which kind of relates to about 50% less nitrogen leaving those fields under long-term no-till. And then this is more of a result that we're really thinking about and want to explore more is the ability of these long-term fields to minimize the phosphorus losses, and whether or not this is true is what we want to test over the long term. I want to highlight the fact that this is preliminary findings. I presented only 1 calendar year worth of data to you here, but just this 1 calendar year worth of data helped us understand these differences, at least at the preliminary levels. So in general, we do see less volume of water leaving these fields. For nitrate, it's very, very encouraging, as you may imagine. But then for phosphorus, the story seems to be more complicated when you're looking at the literature, and we do want to explore this more before we could conclusively come up with any outcomes that we want to really stand by. One thing that Will brought up and I want to bring up here is it's very difficult to compare a field that's under a long-term practice versus a field that's being conventionally managed. The biggest issue that we have is the management is so different because the need of those systems is so different. We at the fields where the farmers have been doing no-till and cover crops for 30, 40 years, they don't need to apply nitrogen as much. They don't apply too much fertilizer. They have less number of passes. So there is inherent differences in the management style and then inputs that go into these systems. And that's what makes it difficult compared to a plot scale research. And what we're really hoping is to study this over long term so that you can kind of make comparisons over a crop rotation time period rather than 1 year or 2 years. So essentially what you want from our study is 2 or 3 crop rotations worth of data to be able to really draw some concrete conclusions, just because the systems are so different. And the other thing that I wanted to mention was the fact that we are hoping to continue this research and delve deeper into the in-field processes, kind of study more in-field processes, the biogeochemistry that happens in the fields, as well as the hydrologic behavior. So that's kind of our future direction for the work, I would say. That's my last slide. I'm going to switch over to our CCA credit slide and then maybe hand it back to Matt.
Yep, thanks, Vinayak. So if you need a CCA CEU, email Elena Whitaker, Elena W, ALENAW at iastate.edu by 5 o'clock today with your name, the name you entered to watch the webinar if different, and your CCA number. And then maybe we can go to the next slide to highlight the webinar for next week. Dr. Laura Alt with Iowa State University will be talking about transport of antimicrobial resistance in ag ecosystems. With that, we'll get back. We'll try to get through as many questions as we can, and hopefully some folks can also follow up with Vinayak and Will later with some additional questions, because very timely topic and lots of questions here. I think you talked a little bit about the management. This first question is for Will. Will, what do you think is causing that conventional management to actually be higher in the coarse textured soils compared to the finer textured soils?
Yeah, so that Northwest Ohio location, both those fields are on a little bit more coarse textured soil, but there is a difference between the conventional fields and the soil health field, where the conventional fields have a little bit more loamy texture compared to the long-term soil health field, which was more on the sandy side of that. So we think that we know from literature, lots of research has shown that soil texture is one of the most important controlling factors on different soil properties like organic matter, microbial activity, these sorts of things. That soil texture has a huge impact, where finer textured soils tend to have more organic matter, tend to have more microbial activity just naturally because of the way those soils are aggregated, the way they hold on to water, the way they can absorb onto the different clay surfaces, things like that. So we think what's going on is it's really just this inherent difference between that conventional field and that soil health field, where the texture is more favorable for holding on to organic matter and for promoting microbial activity in the conventional fields.
Right.
Yeah.
That kind of a follow-on question to that, kind of what you were getting at there, is how do we tease apart, or have you been thinking about how you tease apart the differences due to treatment effect versus the intrinsic soil property impacts?
Yeah, so there's some statistical approaches we can use using texture as a covariate when we're comparing the effects of management. So basically you say, for the samples that have texture similar to each other, was there a difference in management? And so you kind of just focus on trying to bring those, compare apples to apples type of thing. So that's one way we're hoping to get around this sort of difference between the fields.
And we do have, within the fields, we have 2 or 3 different soil types that are represented, and then we do have some textural similarities between the paired field sites, where there are zones within the field that have similar soil texture.
So Vinayak, a question, kind of a 2-part question here. One is, do you know, and have you looked at kind of the inputs, the fertilizer inputs to the different fields to kind of understand whether that is impacting some of the results? And then have you been able to capture information about the about the drainage system design that might also be different, that might be influencing some of the results as well?
Excellent question. Yeah. And the answer on both of those questions is yes. We're just not there yet. We have collected the management information from each of the collaborating farmers. And we're currently working on deciphering all of that information into a schedule of some sorts where we could translate the dates and the different amounts of fertilizers that were applied over time. We just you have to wait at least a year before that management information can be completely processed, just given the delay in us getting the information from the farmers. We actually went further, and we're asking the farmers to provide us even the management data, even for the past 5 years or 10 years, whatever is possible, just to understand the history of those fields better. So that is definitely part of the project. Just we are unable to present that today because we're still working on the data. As far as the drainage system design is concerned, we do have good information on what type of drainage system exists. And with respect to the drainage intensity, there are very similar drainage intensities between the two paired fields, which is a really good thing. So I think we could do a little more on that part, but we do have that information at hand.
Okay, great. Question on your runoff plots or discharge plots. Were there surface intakes on any of the fields?
Really good question. We're still the answer is no. There are no at least especially the numbers that you would expect in a landscape like Iowa is not what you would expect here in Ohio. So the fields that are in Northwest Ohio are very flat fields where we do not have any low spots that needed to be drained with a surface inlet of some kind. The site that's in Southern Ohio, a bit of a topography there, but the conventional field definitely does not have any surface inlets. The long-term soil health field, we're still trying to figure that question out. But as far as I know, if there is one, it's probably just one surface inlet that's kind of right in the vicinity of our where our surface runoff accumulates. But it's not a direct inlet. It's more of a blind inlet type of a situation.
So there's a question here on kind of phosphorus management. You guys might not be able. This might be a topic for Kevin as well, or for some others from Ohio. Maybe we get on a webinar, but I'll bring it up that that DRP leaving the soil surface, and the question: does that suggest that in no-till, instead of applying P to the surface, we should apply enough for both corn and soybean crop in our strip till of head of corn by injecting it in the soil?
I'll give you the water quality side of it, and then maybe Will can chime in. But we have had many studies, including Kevin King leading a research project on 4R principles. The subsurface placement comes to be the most effective practice when it comes to minimizing the losses of phosphorus. So whether do you incorporate that or inject it, and how do you put fertilizer under a no-till system where you're not supposed to disturb the surface, are some of the variables there. But modeling studies conducted by Dr. Margaret Kelsick and that big team also kind of came up with similar conclusions at watershed scales. But then also, I think we have enough evidence, even from the field scale studies, that indicates that subsurface placement is definitely effective. I don't know, Will, if you wanted to add anything to that.
No, that's good, Vinayak. The one thing maybe is, with our project here, kind of interesting, the DRP trends, we think might be showing that the cover cropping is having an effect in terms of potentially increasing DRP concentration in surface runoff. And that's something that some other researchers have shown recently as well. So we think we're seeing that effect. Luckily, the effects of hydrology, where the water is moving, how much is moving, have overwhelmed that sort of DRP concentration increase, so that when you look at the actual loss coming off the field, it's less, even with the cover crops. So I think that's a really important insight we're seeing sort of emerge from at least our first year or two of data. That's exciting.
Right. I think in the interest of being cognizant of where we are with time and respecting the time of our speakers and everybody else that might have something at one, I think we got through most of the questions there. Just want to really thank Will and Vinayak for their presentation today. And hopefully they're willing to answer some questions if folks, have some follow-up questions. And hopefully in future years, we might be able to twist your arm to come back and give another webinar when you get even more information available. And so with that, any parting comments from Will or Vinayak?
Matt, I just wanted to thank you and the Iowa Learning Farms for the opportunity to share our results, and would be happy to come back. In fact, we would want to go back to every place where we presented this and say that, hey, that was preliminary results. Here is more concrete evidence. I just wanted to take a moment to recognize the big team that's behind all this. So I have that slide on the screen here. So Will.
Yeah, thanks a lot, Matt. Appreciate it. Thanks for the platform to get the word out about what we're up to.
All right. Thanks, everybody. Wish everybody a great day and week wherever you're at. And hopefully many will log on next week for our webinar. So thanks a lot.